What do you know about extreme value theorem?
What?
Extreme value theorem. You remember the MVT from Calc 1? What's the MVT? Mean value theorem. Intermediate IVT, intermediate value theorem. So there's an EVT, extreme value theorem. Extreme value means you get extreme values given some conditions. So so F attains an absolute max and min on a closed interval. So that's your condition, is that you have to have a closed interval. Oh, you also probably need F to be continuous. What? Yeah, so you remember testing the endpoints? So the idea is that, just as a simple example, or a generic example, if you have a closed interval from A to B, then you can look at your function and close it off there. And the way you would find the extreme values, you would find the critical points on your function, and then you would find the endpoints. So you find critical points, and then we'll just call it P for critical point. I guess it should have been C, but call it P. And then find the endpoints. I guess you don't have to find it because it's here. And then plug in those values into the original function. So when you plug in the values for the original function, you'll get your y values. And then you'll see that you'll attain an absolute or global within this closed intervals. Max and min, and those are the extreme values that they're talking about. So the key is that for this, you don't have to do the first derivative test or the second derivative test, but you still need to find the critical points. So you find the critical points, and after you find the critical points, you put them into the function and see what the values are. And then you check the endpoints. Put in the value, put it into the function and see what the values are. And then you just compare which one's the largest. Okay? Yeah? Yeah. So when we get to it, and it's going to be the next thing we're going to talk about, it's going to be the same. The generalization is the same, except for a closed interval, you just have 2 points to check, the endpoints. We have to kind of define what a closed domain is for functions like this. So I don't want to talk too much about closed domains because that's a real analysis type of topic that would really be interesting, but you know, somebody can talk about that for like 2 lectures. So instead, we're just going to spend 2 minutes talking about it. So we're talking about the function on a closed and bounded set D in R2. Then you're guaranteed to find an absolute max and min in your domain. So closed bounded set. First of all, your domain is a two-dimensional thing, so we can think about that as a two-dimensional region. And since we are using x and y as our variables, we can look at it on the xy plane. And what you're going to do is you're going to look at your region to see what your region might be. So a region might be a square box over here. So this would be an example of a closed region. Now the key is that for this to be a closed region, we want to make sure we include the boundaries. So it's a region with the boundaries. Closed bounded set. So if you can look at a two-dimensional region with boundaries, then you have a closed and bounded set. So in this example, maybe this could be described as the set xy in R2 such that x is between 0 and 1, and y is between 0 and 1. And when we say between, we're also including 0 and 1 in there. Another example might be on a circle of radius 2, the top half of the circle of radius 2. Maybe this could be described as your points x, y. Such that x squared plus y squared is less than or equal to 2 squared. And as long as we say also equal to, then we're including the boundary. So these are examples of closed and bounded sets. So some examples of things that are not closed and bounded. Can anybody figure out what this thing looks like? It's all ordered pairs in R2 such that x is bigger than 0 and y is bigger than 0. It's all of the first quadrant. We're including the axes, but it's everything else here in the first quadrant. And so this is not bounded, so it's not closed and bounded. What's this thing look like? Oh, maybe I should add the y also. Close, because I added this. These are both have to be satisfied. So what is it? Square in the middle. Everything outside of that. So 1 and negative 1 in the x, 1 and negative 1 in the y. So, but the thing is that it's not equal to the boundary. So we have a dotted line here. And so our first example here is not bounded. And then our second example here is not closed. So those are just two simple examples of things that are not closed and bounded. And for us to be able to use this theorem, for us to be able to guarantee that there's going to be an absolute maximum and minimum on a boundary, we have to make sure that that boundary is closed and bounded, or that domain. Okay? All right, that's your 2-minute that turned into a 4-minute lesson on closed and bounded sets. Now let's go back to the extreme value theorem. And all the extreme value theorem says is that we're guaranteed to attain a maximum and a minimum, absolute max and min. Now we have to look for it. And if you remember back in Calc 1, just a few minutes ago, we were just talking about finding the critical points and then finding the endpoints. Okay? So the tricky part about this is that, well, the critical points are hard enough to deal with. We're going to have to find them. But then the endpoints. We can't just say endpoints for this. So what do we need to do? What are we actually looking for? The boundary lines. So these boundary lines over here will act as our, quote, endpoints, but we have to check every single value that the boundary line is going to give us. All right, so let me just formally copy down what they had in the book. I don't know if I changed this. I remember looking at the book and not liking what they had, so I don't know if I changed it. To find absolute max or min values, continuous function f on a closed and bounded set D, find the values of f. Oh, so here they find the critical points and then they put it in f already. That's what the first one says. Find the extreme values of f on the boundary. So I think I did change it. So find the critical points. So step 1 is actually finding 2 steps. It's finding the critical points and then putting it into the function. That's 2 steps. Step 2 is find the extreme values on the boundary. So find the critical points on the boundary and then put it into f. So another 2 steps. And then the last step is to find, just look at the largest values and the smallest values in the first previous steps. And then that's going to give you your absolute max and min. Okay? So let's see. I think I had some problems set up that I was interested in doing. What did I say? I said something to myself earlier. I'm going to do problem number blah and blah. I forgot. Oh, 29. Let's do number 29. And then what we'll do is after we do this, we'll see if we can see it visually, graphically, because this is still viewable in 3 dimensions. All right, so we imagine that we have a function that we're maximizing. So this could be, I don't know what it could be. Look something up. It could be an area of something. And then we're kind of restricted to this constraint. And so the first thing we want to do is go to the domain, the two-dimensional domain, and try to figure out what this looks like and to make sure that this is a closed bounded set. So it's going to be a closed and bounded set, but it's always all good to take a look at this. On a two-dimensional perspective. So we have 0 or 2, 0, and we have 0, 2, and we have 0, negative 2. 0, negative 2 is over here. Okay, so we have our triangle. That is our closed, and everything inside. So closed triangular region. That includes everything inside. Okay? So now we need to find the critical values. And really, we're concerned about the critical values if they fall within this domain. If we find a critical value that's out here, then we're not going to care about this critical value that's not in our domain because we're bounded within the domain that's given. So let's find our fx and fy, and then we'll set them equal to 0. So fx is equal to 2x minus 2. We'll set that equal to 0. 2x minus 2 equal to 0. And what do we get? X equals 1. Yeah? X equals 1. And then fy is equal to 2y. And then we'll set that equal to 0. And then we got y is equal to 0. So this is nice, and it's to think about this is a paraboloid, and so we're really just looking at one critical point. So that critical point is 1, 0, and that falls right here, right smack in the middle. Maybe that's not exactly in the middle, but that's inside of our domain. Okay? So already, if we want, we can plug that into the function to see if we're going to get a, well, not that we can tell yet, but we'll see what value we get when we plug that into the function. So into our function, f of 1, 0, 1 for x and 0 for y, we get 1 squared plus 0 squared minus 2 times 1, which is negative 1. Okay, so we have a z value of negative 1 at that point. We don't know if that's going to be the maximum or minimum until we check the quote endpoints, but we're really checking the boundaries. So now let's go check the boundaries. So we need to label these boundaries and come up with the two-dimensional equivalents of these boundaries. So we can take each side of this. What am I going to do with colors? Let's use green, sure. Take each side of the boundary as a function of x or y or whatever. So like I'm looking at this line right here. Can you give me an equation, xy relation for that line? This is y is equal to 0. And to be more specific, this is y equal to 0. Wait, what? Let's try that again. What is it? X equals 0. This is x equals 0, where your y value goes from negative 2 to 2. Okay? So let's work with that real quick. And what we want to do is we want to take a look at our function. where we're going to drop x equals 0 on that function. So then this becomes 0 plus y squared minus 2 times 0, which is just y squared. So we can do derivatives and stuff like this, but we're concerned about finding the max and mins for these y values. So what we're going to do is we're going to kind of invoke that extreme value theorem back in Calc 1, where I have this on a closed interval where y goes from -2 to 2, and then I can do the symbolic analysis for that, but I think maybe if I just look at my graph, I can kind of tell what's happening. I have a min at 2 or at 0, and I have 2 local maxes here at 2 and -2. So I will need to consider what color? Maybe a darker green. That looks dark green. I didn't change the color. Did I change the color? Anyways. So I have when x is equal to 0, I have y is equal to 0, y is equal to -2, and y is equal to +2. So now I have, along with my critical point, my one critical point, I have 3 more points to check. We can check that now. So maybe I should label that I did check this one. This is our checking the function. So check. Let's check -2, 0. So f of -2, 0. -2 squared is, I'm just put -2 squared plus, oops. Yeah. So x is equal to 0, y is equal to -2. Sorry about that. So this should be 0, -2, and that's going to give me 0 squared plus -2 squared minus 2 times 0, which is +4. So I have a height of +4. That's bigger than -1. So between these two, I have, looks like -1 would be a good candidate for the absolute min. But then we have to check the other ones. So f of 0, 0, that's this point right here. So 0 plus 0 plus 0, which is 0. So that's between 4 and -1, so this is nothing. F of 0, +2, 0 squared plus 2 squared plus 0 is equal to 4. So it looks like I have another 4 value there. So they look like they're going to be my good candidates for the maximum. All right. I have 2 more sides to check. So let's start with this side over here. Now I need to describe that line as a relation between x and y. So point slope formula, or 2 lines, or however you want to look at it. Go back to Algebra 1 and think about how to find equations of lines. This is just a line, has a y-intercept of 2, it has a slope of -1. So any way you want to do that. Yeah? Because that's x is equal to 0, the function that we're looking at. So right now we found y is equal to this. We're actually going to plug in 2 minus x in for y to see what our graph is going to look like. So we plug x is equal to 0. Should have done this in green. Because of this line right here.
Oh, so that's just a substitution for that region.
Yeah, that's using this equation to substitute so that we have a function of one variable.
So that's the next function.
This is our next function, yeah. And that's exactly what we're going to do. So for our next function, we're going to have f of xy, except we're going to say y is equal to 2 minus x.
This region, you can describe this entire region by saying the absolute value of y is less than or equal to 2 minus x, and x squared is less than or equal to 0.
Less
Or
than
less
equal.
than or equal to 2, greater than or equal to 0.
Yeah. You could do that, but usually when they do triangular regions, they just give you the points. And if the square regions, that's when they use the absolute values, usually. All right, so we have x is equal to x, y is equal to 2 minus x, and then our equation then looks like this. I think we need to FOIL something out. We got x squared plus FOIL it out. We have 4 minus 4x plus or minus plus x squared. Did I do that right? So it looks like I'm going to get 2x squared minus 6x plus 4. Right? So now what we're going to do is we're going to be interested in taking a look at this and find its, oh, by the way, this is good for x values that are between 0 and 2. So what we want to do is we want to find the absolute max and min for this between 0 and 2. So this one isn't as easy as the other one. I think I need to take derivatives. I have to treat this like as a function of x and find derivatives and stuff. So let's pretend that this is a function of x. 2x squared minus 6x plus 4 between 0 and 2. And then, so find a derivative, g prime of x for x minus 6. So x is equal to 3/2 is our critical value. So 3/2, oh, that's 1.5, right? So when x is equal to 1.5, you can figure out what your y value is equal to. So x equals 3/2. Your y value is equal to, what's 2 minus 3/2? Is that 1/2? 1/2. Okay, so we have a critical point in the boundary So what do we need to check? We need to check this critical point, we need to check this other boundary, and then we technically would check this boundary, but we already checked that, and we got a y value of 4, or z value of 4. So now we have just one less thing to check. Well, we still need to check two things. Check f at 3/2, comma 1/2. All right, you guys might need your calculators here. So this is 3/2 squared plus 1/2 squared minus 2 times x. X is 3/2. So 9 plus 1 is 10, 10/4. Minus 3, 10/4, 5/2. 5/2 minus 3 is negative 1/2. So negative 1/2, which is not any less than negative 1 and not greater than 4. So that's not going to play into what we're doing. And then the other one is 2, 0. That's our other endpoint over here. So we put 2 in for x, 0 in for y, and then 2 for x again. So we have 4 minus 4. That's equal to 0. So this is 0 again. It doesn't play a part. Okay. We got one more side. Need another color. What color? Pink. Wonder if you can see pink. So we have one more side. Y is equal to, this has a positive slope. Slope is 1. And then the y-intercept is 2, or negative 2. And again, your x goes from 0 to 2. This is getting to be a long page. So f of x comma y, where y is equal to x minus 2, will give us an x squared plus x minus 2 squared minus 2x. And if you FOIL this, I think you're going to get the same thing, aren't you?
It's just that value squared.
Yeah, and it's the negative of that. So plus dot 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 equals 2x squared minus 6x plus 4, and I just copied this. And again, we're going between 0 and 2. And since we know from our analysis that we get a critical point, maybe I drew that line too thick. We know we're going to get a critical point there, but I think the y value is going to be a negative instead. So we're going to get our critical point x is equal to 3/2 and y is equal to negative 1/2. But there normally would be two other points that we would check, but we already checked these other 2 points, right? So that's done. So we only really need to check that last one, which really won't give us anything because it'll give us the same result as this. So if we put 3/2 and negative 1/2 into the original function, This is the only difference is that this negative 1/2 and positive 1/2 are being squared, which will result in a positive 1/2. We're going to get the same result. Just check. Which did not give us a number less than negative 1 or a number bigger than positive 4. Phew. So in the end, absolute max is 4, and that happened where? So 0 and 2 and 0 and negative 2. So your absolute max is going to be at 4. It happens at 2 places. Your absolute min is negative 1, and it happens at, where does it happen? At our critical value, 1, 0. Okay? Wow. That was a lot. What? All right. I was thinking of doing another example. Let's see if I can do this in less than 10 minutes. Number 35. Oh, you know what? I think I did something wrong. This example over here, I only took the top half of the circle, so that has to be y is bigger than 0. So make sure you add that in your notes if you're taking notes. By the way, have you guys ever thought about not taking notes? Because, I mean, the notes are up here, right? You save them. Yeah, so I don't know. I encourage you to try that one day. Just don't write anything. Just focus and get into it instead of writing down and trying to have to rush to copy something. Because the notes will be available for you. No, you don't have to do it now. But I encourage you to try that just one time, and then that will make you go to the website and look for the notes and download it and print it or whatever, or copy it. Even better, copying it after it's done might be a good exercise. And then if you get lost, you know, the video will help re-engage you. Is this third and fourth power? Okay. All right, so let's take a look at these. This problem. The domain this time is a circle, a unit circle, or a disk, I guess, because the unit circle is just the boundary. But if we want the inside, we usually say the disk because it's filled in. So this is our boundary, or our region. Yeah.
So let's say we have like 2 concentric circles there, and we want to find. So what if we are doing the area outside?
If you have 2 concentric circles and you want to find the boundary within those circles, you would do the same thing. You would check for the critical points that's within that strip. I guess that would be a washer, or it's called an annulus. You would look for any critical points within that annulus, and then you would check the boundaries by checking the 2 circles. Okay. And actually, that picture will come up for us later on when we're doing integrals, and then we'll find a nicer way to approach that. Okay, for now we're just looking at this disk, and then this is our function. And so the first thing, remember, is to find the critical points and to see if there's any critical points within this region. So let's find the critical points by taking the partials. 6x squared. We're going to set that equal to 0, so x is equal to 0. And then fy for y to the third equal to 0, which is y is equal to 0. So we got our critical point right smack in the middle of our disk. And we might as well put it in now. So what happens when we put 0, 0 into the original function? We get 0. Okay, so this could be a max, it could be a min. It'll depend on what happens when we check the boundary. Now, our boundary looks like this. X squared plus y squared is equal to 1. So if you just check the boundary, I guess I should do a different color now. We're going green on this. So this boundary is x squared plus y squared is equal to 1, as opposed to less than or equal to, because that's the whole inside. So just equal to 1. And I was hoping maybe that I could just drop either x squared or y squared into here and then try to see if I could solve for it. But it'll be kind of difficult to solve for y to the third power to replace this. But y to the fourth power, if I just solve for y squared here and then square that, then that's what I could put into y to the fourth, because this is equal to y to the fourth. Okay? So the idea is to somehow rewrite your function, your original function, as a function of just one variable instead of two. So if I replace this y to the fourth with 1 minus x squared quantity squared, then I'll have this function as just a function of x. So I have 2x to the third plus y to the fourth, which is 1 minus x squared quantity squared. And so I'm going to FOIL it out so I can take the derivative easier. And then I'm going to call this, maybe I'm going to call this g of x. Say that it's just a new function of one variable x. So I got 2x cubed plus 1 minus 2x squared plus x to the fourth. So now I can find the derivative, find the critical points, and then, oh, by the way, I didn't say that this is going to work for your x values between -1 and 1. Right? That's how my x value is defined between -1 and 1. All right, so let's find the derivative. G prime of x equals 6x squared 0 minus 4x plus 3, that's 4x cubed. And I have to set this equal to 0. Oh, is that easy? I can factor out 2x. And now let me write it in order. So I'm going to write this first. 2x squared, I'm going to write this second, plus 3x, and then this thing last, minus 2 is equal to 0. So I got x is equal to 0, and this thing, can you guys factor this in your head, or do you have to use the quadratic formula? Is this factorable? So 2x minus 1 plus x, you can FOIL that out to make sure that it's going to work. Looks like it'll work. So this is x is equal to 1/2 and x is equal to -2. Well, the good news is that we can knock off one of them because this is not in the domain. And then, but we have 1/2. That 1/2 would go into this function to figure out, to get us our y value. Can it get, yeah, I think it can just go in the g function. Because if we put it in a g function, that gives us our z value, right? I think you're right. So let's do that. So this will be equivalent to checking. So check x is equal to 0 by putting it into the f function or the g function. This is going to be 1, right, when we put 0 in. So there's an x, and there's an x, there's an x, so all that's going to be left is 1. And then we'll check x is equal to 1/2. G of 1/2. That one's a little bit more difficult. So 2 times 1/2 plus 1 minus 2 times 1/2. Oh, this is to the third, this is squared, plus 1/2 to the fourth. So 8 and 1 cancels, right? So it's 1/4 plus 1, 1/4, 1/2, and 1/16. Did I do that right? Am I missing something? 8, 9, 4, 9 plus 4. 13 over 16 is what I got. Is that right? So that's between 0 and 1. It's not 0, it's not 1. So I think we have a maximum value of 1, and it happens at x is equal to 0. Oh, what's the y value? We didn't really find the y value. Can you guess what the y value is? Well, 0, 0 is a different point that we checked earlier. 1. And then we have a minimum value of 0 at, where's this one? This one's at 0, 0 up here. Okay? I think this is also -1 also happens. Because if you look at putting the x value of 0 into the function, you're going to get when x is equal to 0, you have two possible y values on the boundary. Okay? I wanted to show you a picture of this too. And so f of x, y is equal to this function is some sort of surface, right? And we're trying to find the highest point in that surface at some given value. So what we need to do is, or what we can think of is when we plot the surface, I don't know, what's that look like? Whatever it looks like. Let's go with a baby car seat. And then, so what we really need to look at is this thing within the boundary. Now, the boundary is two-dimensional, right? But if I graph x squared plus y squared is equal to 1 in 3 dimensions, do you remember what's going to happen? What? Not a sphere. Cylinder. It's going to be a cylinder. You got the circle in the xy plane, and that's going to get swept because there's no z, right? So if I graph that, x squared plus y squared is equal to 1, it's going to give me a cylinder. And hard to see. Let's see if we can change colors and do some other fancy stuff. But what we're concerned about, or what we're looking for, would be, ooh, I think we got something wrong here. What we're looking for is we're going to try to ignore everything else that's outside of the cylinder and just focus on what's inside of the cylinder. And we're trying to find the maximum and minimum values in there. And now that I'm looking at it, I think we might have done something wrong because I tried to take a little shortcut. And I'm seeing a maximum value that's all the way up on top. So I need to freeze it here. I'm seeing the maximum value as being this point up here, and then the minimum value as being this point down here. So I think we might have done this incorrectly. And there's that little dip in the origin that gave us probably a local max or a min, or maybe even a saddle point. But within this whole enclosed boundary, our local max and min has changed a little bit. Not has changed, but it's obtained a little bit differently. Yeah, it looks like it might be 1. Yep, that could help. What is it? 0, 1, 1? No, that wasn't even right. Yeah, maybe we shouldn't have plugged it into the G. We also needed to have plugged in x is equal to 1 and Oh, we did 0 and 1/2, but we didn't do the endpoints. Ah. All right. So let's backtrack here. So we need to check endpoints. So the endpoints are x is equal to -1 and +1. And to get your corresponding y values, remember that this is the equation that helped us find a relation between x and y. And actually, or we can just look at the point on the circle, right? So when x is equal to 1, what's y equal to? 0. When x equals -1, what's y equal to? 0. I think I said that backwards. We take these points away. So these are the points that we need to look at. So when x is equal to -1, y is equal to 0. When x is equal to +1, y is equal to 0. So we're going to check those 2 more points. Good thing we graphed it. So back to our original function. Our original function is 2 times x cubed plus or minus plus y to the 4th, and y is equal to 0. So this is going to give us a value of 2. -2, right? 2? -2. So that's less than 0. So now we found our minimum. F of 1 comma 0 is going to be 2 times 1 plus 2 times 1 to the 3rd plus 0 to the 4th, and this is equal to 2. So this is our actual maximum. All right, so I'm going to take a picture of this, but this time let's put the correct points in. The point was 1, 0, and 2. And then the other point was -1, 0, and -2. So that looks better. Is it viewable? Can you see it? I don't know what color to use. That's fine, I suppose. All right. So we're going to need this information about finding the max and mins at the boundaries when we talk about our next topic. But we need to, I need to talk about one more thing. Max is 2 at 1 comma 0, and then the min is -2 at -2 comma 0. Okay? Yeah. Now is it okay? All right, good. Okay. Now, we're going to backtrack a little bit, and then this is, again, some information that's going to help us go forward. I don't know if this is enough time, Trevor. So I've said that gradients are perpendicular to level curves. And at some time, I've kind of hinted that gradients are perpendicular to level surfaces. So I'm going to say that gradients are perpendicular to level sets, and then you can replace the word sets with whatever's appropriate. So you would use the word curves if the function you're talking about is a function z is equal to f of x, y. And then you would replace the word sets with surface if now we're looking at another variable is equal to f of x, y, and z. And anything higher than that, you just have to imagine it as something that's higher than 4 dimensions. Okay? So what does that mean? That means if I have a function w is equal to, and I'll try to keep this simple with x squared plus y squared plus z squared. This is a function that goes from R3 to R. So if we want to look at this as a function, I didn't call it a proper function. F goes from R3 to R. And then if I take a look at W equal to 1, for example, a constant, any constant, then I'm going to have 1 is equal to x squared plus y squared plus z squared. What is this? This is a sphere, right? Sphere. More specifically, this is a surface in 3D. More specifically, this is a level surface in 3D when W is equal to 1. So just like you have a surface, if you have z is equal to f of x, y, you're going to have a surface. And then the level curves are curves in 2 dimensions. They go back to their domain, the dimension of their domain. Similarly, if you have a function of 3 variables that outputs another variable, you technically are living in 4 dimensions because you have 3 variables going in and you have a 4th variable coming out. So that's 4 variables that you're dealing with. But when we're taking a look at a level set, in this case it's a level surface, that level surface will live in the domain of your function. which is in this case in 3 dimensions. Okay? And so the key thing that we're going to continue to talk about next time is that if you take the gradient of this, which is going to be 2x, comma 2y, comma 2z, just took the derivative with respect to x, and then with respect to y, and then with respect to z, then this is your gradient. The gradient is going to be perpendicular to a level set. And in this case, it's a surface, so we can find, we have a perpendicular to a surface, which means we should be able to find tangent planes. Okay? So that's how we're going to start tomorrow after you take your quiz. We're going to start talking about tangent planes for implicit functions.